Part 4 deals with physical layer design, in particular with transparent physical layer design, where I decided to split that from the regenerative case because a lot of contributions are available today. Generally, it is very important to understand the physical layer because it facilitates us to optimize the system and also to synthesize certain system parameters. A lot of different highly complex contributions are available today on the transparent physical layer design, so I'll just concentrate on a few of them, and in particular we will discuss the optimum relay function, we will discuss certain canonical topologies, and the spacetime trellis transceiver design. Talking of the optimal relay function, references 61 and 62 question the optimality of the transparent and regenerative relay functions. So they came up with an optimum function which is valid for the configuration where you have a source X transmitting to a relay which performs a certain relay function fx plus a certain n1, and that goes to the destination here, where the destination adds its own noise n2. It turns out that the SNR optimum relay function, if you use BPSK in the memoryless relay channel, is of that form here, which can be decomposed in two parts. One is a power scaling and the other is the amplitude transfer, which is a tangent hyperbolicus here to the input R, where PS and P are the source and relay powers respectively. Now that is just a starter in my opinion, because it does not include any fading nor any shadowing, but gives us a good insight into the optimality of the relay function. So we have here, if we depict the relay input-output relationship, where we relate the input to the output, I depict three cases. The first case is the amplifying forward protocol, which is a straight line as we expect because it just scales the input to the output. The green line is my regenerative single estimation protocol, meaning I'm just receiving something below a certain threshold and I transmitting it to be as -1, and below that threshold I transmit it to be 1. Contrary to these two, the optimum SNR relay function is that red one here, the tangent hyperbolicus shape, which relates input to output, and it reminds us of a very cheap power amplifier. So maybe dirty RF with very cheap power amplifiers yields quite a close optimum relay function. Now let us move on to performance analysis, and I will go now to a few canonical topologies. First topology, where source transmits via relay channel to relay and via another relay channel to destination. So following 43, we assume a 2-hop relay, a single relay. It's a fixed gain relay, so it does not adopt its relay coefficient. We assume relay fading channels, and we don't assume a source to destination link. Now the results I'm going to show you are results for the moment generating function MGF. They are in closed form, but most error rates still remain in integral form, which I'll explain in a moment. According to 43, you can express the end-to-end signal-to-noise ratio gamma with a fixed A, with a fixed gain A, in this form here, which is the harmonic mean. So it is gamma 1, the SNR of the first link, which is given here, multiplied by the second one, divided by a constant, which is given here, and which is the result of a few power normalizations along that chain, and plus gamma 2. Now that term here allows us to find the moment generating function of that SNR, and that is given right here. And then with that moment generating function term, you can calculate the bit error rate. For instance, in binary differential BPSK, it would phase shift keying, it would be 1/2 M of 1. If you have more complicated modulation schemes, still an integration would be involved, which probably is not that straightforward because it involves tabled function like the exponential integral function here. Now, how did we arrive at that expression here? And I'll show you that in a subsequent slide. The best way to proceed is to go via the outage probability. So we ask, what is the probability that my end-to-end signal-to-noise ratio gamma falls below a certain threshold, gamma threshold? To do so, you would have to go through the joint probabilities or equivalently through the marginal probabilities given here. So it is the integral going from 0 to infinity of the outage of the probability that that term here falls below a certain threshold, given that my second channel realization gamma 2 is fixed, multiplied by the probability density function of that second gamma 2 and the integration over all possible states. Now that term here, that probability here, is nothing else but the CDF of my first link given gamma 2 fixed, which, if you do the mathematics assuming Rayleigh fading channels, is that expression here given in these brackets, and then you multiply that by the PDF of gamma 2, which is that expression here, and you integrate this and arrive at that term here. What we do now, we replace the gamma threshold by gamma, and we obtain the PDF by differentiating with respect to that gamma. So the term we obtain from the outage is that one here. To obtain finally the moment generating function is done simply by using that expression down here. So we plug in that probability density function we derived into this expression down here, and finally we obtain 14. That is the first and only time I show how to derive the moment generating function. For all subsequent topologies, you would need to proceed in exactly the same fashion. Now, as for topology number 2, we will follow reference 63, and the difference to the one before is that at the destination we got a receive antenna array, and that has now n receivers, which is bigger than 1. Closed form results are asymptotic and hence only hold for high signal-to-noise ratios. Assuming two different cases, one is the constant amplification using coefficient 6, which I had shown when I presented you the channel, and the variable amplification using 7 from the very same section, we obtain the symbol error rate following the moment generating function approach in that form here, which cannot be calculated in closed form, but we can find an upper bound which is given right here, where m is related to the modulation, n is the number of receive antennas at my destination, P1 is the transmit power, n is the noise power, and that n here is the number of antennas. So what we see is that in this case the diversity order is only n plus 1, because my power, my signal to noise ratio, scales with to the power minus n plus 1. If we go from constant amplification to variable amplifications, we get an expression which is given here. Now the authors in that paper did not evaluate this expression. It is actually to be obtained in closed form, but they found a bound and showed that this one here behaves in the form 2n. That means it gives you the full possible diversity order of 2n. If we plot now here the signal to noise, the symbol error rates versus the source to destination signal to noise ratio in dB, and we look at different cases here. Let's look, the blue line here is the fixed gain with 2 receive antennas. That one here is a variable gain with 2 receive antennas, so that has a diversity order of 4 actually. I remind you it is 2n, so variable gain would be 4. Whereas with a fixed gain and with 3 received antennas, it is also 4 because it's n plus 1. So as you see, it has the same steepness, the same diversity order. But in the case of a variable gain, you get away with less receive antennas. But the disadvantage is that you would need a feedback channel to feedback the instantaneous channel gains. Now as for the topology number 3, we follow 64, and the difference here is now that we don't use just a single relay, we use k relays, and we also have a line of sight, or sorry, a direct connection between source and destination. And as it turns out, we have an exact integral expression for the symbol error rates, MPSK, assuming maximum ratio combining, and we got some loose closed form upper and lower bounds, which neglect the noise at the relays. Now let's look into details here, and what we find and what is the most important thing to bear in mind here is the end-to-end signal-to-noise ratio, which can be expressed as gamma naught, which is a signal-to-noise ratio due to the direct connection between source and sink, and the signal-to-noise ratio, which is due to the K relays here, where each of these gamma Ks is the harmonic mean given right here. Now, as it turns out, you can calculate using exactly the approach I told you before to find the moment generating function and the integral expression for the symbol error rates, but instead the authors in 64 found very nice upper and lower bounds for the error rates, which are given right here. And as it turns out, for the expression where you have the signal to noise ratio, you got it to different exponents, and we see that the upper and lower bounds are given right here. For instance, for the K, that you have 3 relays, that is the red curve here, and that is the lower bound, and that one here is the upper bound. And as you can see, these bounds are very loose, but they give the right tendency in terms of the signal to signal error rate behavior versus the source to destination signal to noise ratio. Now, if we move on to topology number 4, apologies, and that follows the exposure in reference 65, we assume now K serially concatenated relays. We don't have any connection between source and destination directly, but we assume very general fading channels such as Rice and Aghvami, and it turns out that 65 derived the optimum fixed relay gains, and it derived a fairly good upper bounds on the end-to-end signal-to-noise ratio. In particular, the author of 65 realized that the end-to-end signal-to-noise ratio can be expressed in terms of a harmonic mean, which is given right here. Gamma 1 is the signal-to-noise ratio of the first hop. That is gamma 2 of the second hop. The coefficient C had been given before, and it turns out that that expression here can be expressed in very closed form right here. Now it turns out that that signal-to-noise ratio expression is fairly intractable. So an interesting approach had been proposed that we upper bound the harmonic mean by the geometric mean, which is given right here. And in that case, you can actually express the end-to-end signal-to-noise ratio gamma in that form here. Now, with that expression in mind, which is a product term multiplied by a constant z here, we can derive the optimum gains relay coefficients, for instance, for an Aghvami M channel, which is given right here, which obeys a few power constraints and gives you optimum performance at the receiver. It also allows you to calculate the M statistical moments, which is given right here, and with these moments you can calculate error rates, outages, either in closed form or by using approximations of convergent series of moments. Let us move on now to topology number 5, and we follow here paper 66. It is a fairly generic topology where you have a few relays in parallel and a few relays in concatenation in serial. You also have a connection between source and destination, and we assume maximum ratio combining at the destination. Now the forms which have been the equations which have been derived, they neglect the noise in the relays, and they're also only asymptotically tight for large SNRs, but they give quite an interesting insight into the behavior of such systems. In particular, let's look at a simple system where you have just a single relay and a direct link, and here we have the signal to noise ratio given here, which again is the harmonic mean plus the signal to noise ratio of the direct link, And the symbol error rate, the SER, can be calculated using that expression here that is quite well known, using the Q function multiplied by the PDF of the channel here, the signal to noise ratio, and that coefficient K within the Q function depends on the modulation scheme. Now 66 has observed that QK gamma drops rapidly to zero for fairly large gamma and gives hence very little contribution to the kernel. What they've done is they have hence resolved that PDF close to its origin into a Maclaurin series and used that approximation, that expansion, to find an upper bound on the symbol error rate, which is given right here, and where you see all necessary terms given in here, where the A depends on the channel. For instance, the Rician K channel gives an upper bound signal to a symbol error rate, which is given right here. Now, the interesting thing is that upper bound increases with K increasing, meaning with the channel becoming better, my symbol error rate actually goes up. Now, that is an interesting mystery, and I'll leave that for you to solve it. Let's move on now to the space-time transceiver design for the transparent architecture. And a few contributions have emerged recently, which I will not be dealing with. For instance, 67 deals with a noise reduction scheme at a transparent relay. 68 proposes a unitary precoder. 69 uses lattice-coded cooperative schemes over non-orthogonal amplifying forward protocols. 70 proposes novel space-time block codes, which optimize actually diversity multiplexing trade-off of the channel, and 71 proposes equalization methods for various cooperative space-time block coding diversity schemes over frequency-selective fading channels. Now, we will stick to the transceiver design using space-time trellis codes, and these have been analyzed in 72 a while ago and later kind of redesigned in 73. And the question we pose is, what type of space-time trellis codes do we need to design if a source transmits that space-time trellis code word via a bunch of relays which just transparently relay that to a destination, which also may have a few receive antennas. As an example, we do have N transmit and M receive antennas, and using the well-known Rankine determinant criterion from Taroch, which applies if the product of M by N is smaller than 3 actually, you can upper bound the average error probability if C has been sent that a sequence E, an erroneous sequence will be received, will be upper bounded by this term here, meaning we need to find the expectation over all possible channel states of that system, assuming that code word C has been generated but code word E has been received. Now that is quite a well-known equation here, and we find up here an eigenvalue that is the ith eigenvalue of the distance matrix A, which is composed of B, where B denotes B is given as a difference matrix for the code words, meaning if I generate a code word E and I receive code word C, then that difference matrix is given right here. Now, P beta is the probability distribution of my entire N by M dimensional random channel, and for arbitrary channel realizations we can upper bound that term actually. We look at that expression here and we apply Schwarz's integral inequality, and using that integral inequality we effectively show that the pairwise error probability can be upper bounded by that expression here, which gives us exactly the order of M multiplied by R, which means that you need to have the codes in place which Now, P of beta is the probability distribution of my n by m dimensional random vector. And it can be shown that we can upper bound that one here by interchanging the product and the integration by this term here. So the pairwise error probability is given like by this expression here, upper bounded by that expression here. Now in addition, if we define the g to be of that form and x of that form, and we use Schwarz's integral inequality, we can actually show that this pairwise error probability can be upper bounded by that expression here, where we have m to the power r right here, where r is a number of non-zero eigenvalues. So therefore, the minimum determinant of all code word difference matrices needs to be maximized, and therefore, if we have designed a determinant, a code which follows a determinant criterion, it will also be good for our transparent relaying channel. Now we designed such codes and have come up with a few performance graphs here. We have depicted here the frame error rate versus the signal to noise ratio for various families. So the black family is where you don't have any relay terminal, but you go increasing the states of your space-time trellis code from 4 to 8 to 16 states. The blue curve now uses one relay where it goes again 4, 8, and 16 states. And finally, the red curves are facilitated by two relaying mobile terminals. Now, as you can see, the codes behave well, and the relaying terminals increase the performance of my space-time trellis coding system. Now with that, I finished the part on the transparent physical layer design, and we will move on to the regenerative physical layer design.